the second last lecture. So what we are doing today is finish up, hopefully, the network protocol section. So we have two chapters left in our networks part. Um, Let me just go to the table of contents. So we are close in finishing the network protocols. There are two main topics missing. The first topic that we are doing in the first half of the lecture today is um, seeing how routers do a routing decision. So not a routing algorithm. A routing algorithm technically is an algorithm to fill up the routing table, but the algorithm a router performs in order to make a routing decision. And this algorithm is topic of the first half. And then the second half will be the transport layer, because we didn't discuss the transport layer yet. And with the TCP protocol, there is a very dominant protocol in internet technologies and networking that we will take a closer look at. Okay, before we start into the network protocols, one small remark. So last week, I unfortunately um, had to abort the lecture, and I uploaded the solution to a very important task. Um, Very important because it's very suitable for an exam question. Blink, blink, blink. You know what I mean? Um, and this is the network segmentation task, exactly. And this is a nice task. It's perfectly suitable for the exam, and I uploaded the solution, but the solution was a previous draft of the solution, and there were errors in the solution. I corrected the errors and re-uploaded the solution PDF. So if you downloaded that PDF before, please download it again in order to have a better solution. I mean, the solution was fine-ish, but at some places it had some errors. But now it should be good. Um, okay, so let's switch over to our slide deck, and we continue exactly where we left off last time. Um, and yeah, before we go to the first like technical term that we introduced today with the subnet mask, um, small like reminder, yeah, here. Um, Small reminder on IP addresses. So remind that an IP addresses has two parts. It has a network portion, which identifies the subnets in the upper bit, and we have a host portion. And the host portion is the IP range in a subnet where the addresses inside that range, except two addresses. The first address is the network address, and the last address is the broadcast address, but everything in between can be allocated and assigned to a host. So we have a network portion and a host portion. The size of the network portion defines the size of the subnet, and both network portion and host portion sum up to 32 bits. So for example, if you have a network portion of 8 bits, you have a host portion of 24 bits because the sum is always 32 bits. And then last time we talked a lot about subnets and the CIDR notation, so the way we combine the two informations, like the actual IP address itself, but with an IP address, you cannot determine the network portion, how long the network portion is. And in order to tackle that, we have the CIDR notation, CIDR, classless interdomain routing. And the CIDR notation separates the actual IP address with a slash and the number of bits in the network portion, which we also call prefix. So the prefix is the number of bits in the network portion. And we have with the slash separated the IP address and the prefix of the respective network, because the prefix is an identifier or gives you the information how long or how big the subnet is, how long the network IP address range is, because it defines the network portion, right? So if you have a prefix of 8, That means the first 8 bits are for the network portion, and the remaining 24 bits are for the host portion. So the range of IP addresses in the respective subnet, it starts from, in this example, 192.0.0.0, and it ends in 192.255.255.255. Okay. And then we talked about a method in order to design a subnet allocation. So given a larger network, how can you place your subnets in a larger network in order to satisfy these two design goals, placing the subnets in a way that they can easily be expanded and maximizing the remaining addressing space. So these are goals that we desire, and balancing these two goals is a challenge, as we saw the last time. And the best method to tackle this challenge is the reverse binary method, which I will not go into details today. Because I will start the new content for today with a new term, which is the subnet mask. The subnet mask is similar to an IP address in a sense that it is a 32-bit binary number, but it does not constitute an address of a host. It's rather a different way how to write up or to represent the prefix, meaning the network portion of a address range. And an address range is a subnet. So basically, the subnet mask is a representation of the size of a subnet. And it has 32 bits as an IP address. And it has leading 1 bits equivalent to the length of the prefix, so equivalent to the length of the network portion, and the remaining bits in the host portions are 0. In this example, what do we have here? We have 24 ones in the subnet mask in this binary number. And as the total sum is 32, the zeros that are coming after the ones are 32 minus L, whereas L is the length of the prefix, and this is 8. And maybe you have seen this kind of addresses already. Subnet masks are as IP addresses written up in dotted decimal notation. That means we have 32 bits. We divide them in 8-bit groups. We call these 8-bit groups either octets, or 8 bits are a byte as well. So we have 4 bytes separated by a dot in the dotted decimal notation. And for each group that we have, we represent the binary number, which is 8-bit long, in decimal format. So this subnet mask with 24 ones and 8 zeros is written in dotted decimal notation in 255 to 55 to 55 0. Question, why do we need the subnet mask? Well, main topic of the first half of our lecture today, the router needs to extract the subnet address or the network address of a host address, and therefore a router needs to know the prefix. And typically in routing tables, the prefix is stored as a subnet mask. So let me get back to one of the early slides of the network layer in order to remind you what routing is all about. So here we have it, a minimal example with 3 subnets and 4 routers. Information number 1 is routing works by selecting a next hop, and this way hopping from router to router through subnets and subnets until we reach the final destination. And this next hop calculation is done by a routing table. So we had this example with router 4, where we take a look at the routing table. So if the destination, so assuming a IP packet arrives at router 4, right? An IP packet, where's the header here? The IP packet except for the payload, obviously. An IP packet has these information in the header: source address and destination address. So we know where the packet comes from, and we know what is the final destination for a IPv4 packet. So when a packet arrives at router 4, which is addressed, for example, to an address that is in the range of subnet A, then we determine the next hop from router 4 to router 2, basically passing subnet C. Or if the destination address in the packet that is arriving at router 4 is an IP address that is in the range of subnet B, then we hop, so we jump or forward the packet from router 4 to router 3. And as router 3 is part of this subnet B, the router 3 can then deliver the packet. Be careful, this line does not mean that this subnet is somehow connected to this router, and this router is a device, something in between two subnets. This is a part of relationship, meaning that router 3, for example, is at the same time part of subnet B and part of subnet C. And this way, because routers are part of many subnets, you can build up a chain of packets jumping from router to next router to next router to next router, and this way passing the subnets until the final destination is reached. But this is how routing works. Information one is a routing decision means, from a perspective of one router, what is the next hop? Like, what is the next router before the packet to? And the second information is that this calculation is done based on a mapping from what is the actual target subnet and what is the next hop in order to bring the packet one step forward to this subnet, right? So we are talking about subnets. Wait a second. I have a pretty high CPU load. Is the stream still fine? I don't know what's causing the high load. I also see a lot of network activity. So let's see. If something is bad, you let me know in the chat. Maybe some update or whatever. Okay. So in conclusion, in order for a router to make a routing decision, the router needs to know the subnet of the final destination, more precise, the network address of the network, or the network address of the subnet the target IP address is in. And the router needs to calculate that. And for this calculation, jumping slides, exactly for this calculation, we need this. Feature is pretty simple. You have an IP address, and just by looking at the IP address, you cannot derive how big the subnet is. And more importantly, what is the network address of the subnet? To remind you, the network address of a subnet is the first address in the range of addresses in a subnet. What a router does here, it ANDs together the IP address, which is in the destination address field of the IP header, and the subnet mask is known to the router because this is a configuration parameter of the subnet. So this is basically known at the router, and the router ANDs these two values together, like a Boolean AND in binary, in binary, right? By the way, this subnet mask is a prefix of 20. because 255 is 8 ones. So we have 8 ones in the first octet. We have 8 ones in the second octet. And then we have a value of 240. It's not as common as 255 or 0. So these are like default values in a subnet mask. 255 is all ones, and 0 is obviously all zeros. But 240, let's convert this to binary really quick. Binary to decimal. I mean, I know the answer, but to show you. Binary, no, decimal to binary, a value of 240 if we convert this. Oh, waiting for Google Analytics. I do not want to participate in any Google Analytics. Can you see that my browser is like waiting for Google Analytics? Okay. I guess you have to trust me that it is. I will write it in chat. 4 times 1 and 4 times 0. So this decimal number equals to 240 in decimal. So the top one is binary, the bottom one is decimal. So if we have 8 in the first octet, 8 in the second octet, and 4 in the third octet, the number of ones in the subnet mask is 20. So we have a prefix of 20. In order to express this inside a notation, we separate the IP address with a slash and the length of the prefix, which is 20. Now, let's calculate arbitrary host. So we do this in binary, meaning we start from left to right, because left is the most significant bit, and then we compare these two, right, and calculate a logical AND. You remember a Boolean AND, Boolean and logical is the same, Boolean AND is a operation with 2 operands, and if the 2 operands are 1, the result of the operation is 1. And if either of the operands is 0, the result is 0. So 0 and 1 is 0. Next is 1 and 1 equals 1. Nice. Next one, 0 and 1 equals 0, and so on and so forth. So in binary, you AND the digits, the binary digits from the IP address and the subnet mask together, and this is the result then. You can sometimes when the subnet mask is 255 or the subnet mask is 0, you can directly derive the results. Let me show this to you. For that, I need to prepare my tablet, which should be set up already. Does this work? Yes, this works. So what do we have here? We have, for example, 91.39.190.46 and the subnet mask. We end this together with 255, 240 and 0. And if the subnet mask, I will mark this with green. So for example, if the subnet mask is 255, then we know this is all ones, right? And if you AND something together with all ones, the result is always the first operand. So 91 and 255 in binary is 91. Right? Because this is the first operand. If the second operand is 255, the result is the first operand. Vice versa, if we take a look at what color do I? Yeah, yellow is fine-ish. If you consider the 4th byte, the 4th octet, with 46 and 0, if the subnet mask is 0, then something crashed. You can still see and hear me? Yes, okay. My slide deck just crashed. Something's going on with my computer. I don't know what it is yet. But we have 64 and 0, and the result is always 0. And this way you can easily derive the first octet, the second octet, and the last octet. The third octet is a little bit tricky because 240, again, it's 4 times 1 and 4 times 0. And I don't know by heart what 190 is in binary. So you would need to do this like manually if you are asked to do so in an exam. But I have prepared this. Oh, my slide deck crashed. So let me restart real quick. What do we need? Need network. This over there. Refresh this window. Yes. And then go through all the pages in this slide deck. Where do I have my example? Ah, right here. But if you convert it back to decimal again, then you see, well, again, the first octet is clear, the second octet is clear, the third octet is not obvious, and the third octet is clear, and the prefix is also clear. So adding these two numbers together, so 190 and 240 in binary is exactly this number. It's 176. So you see, this IP address or the network address is in the third octet different from the IP address because we have a relatively big prefix with 20. So you cannot easily like see how the network range is actually. We can look this up. So 91.39.176.0/20. I try to remember this. There are some nice tools to calculate subnet ranges. Subnet calculator. Oh, restart. What? Don't want to restart Firefox. I want an IP subnet calculator. I have to restart Firefox. I guess I know what's going on. I guess that some update routines are just running and updating the programs that I'm using for streaming, like my browser. Subnet calculator. Now, our IP address was 176.0, and our subnet was /20, which is a subnet of 255.255.240.0. Then we press calculate, and then you see here, this is the range. So the range of this subnet ranges actually from 92.39.170.1. This is the first usable address because the network address is 0, and the broadcast address is the last one in the range, which is 91.39.191.255. So the range of usable addresses is this one. The total number of addresses is 4K, so 4069, so it's a power of 2, which means we have a number of usable hosts of 4094 because we need to extract the network address and we need to subtract the broadcast address here. This is how we come to the values. Okay, so this is what a router does in order to find, given an IP address of a host and given the subnet mask, this is the way how a router calculates the network address. And the network address is required in order to do routing decisions. And we do this by this running example. So let's take a look at this slide. This slide is a more refined version of the network diagram that we had in our first network lecture. So this diagram has subnets. Subnets are these orange clouds there. So we have a subnet 198.120/16. We have 129.000/8. We have 91.39.176/20, then 50.12.230/24. And then we have routers in there. We have a router A, B, and C. And as a router, like this line here means that this router B, for example, is part of the 91.39/20 subnet, meaning if this router is part of the subnet, this router also has an IP address of the subnet. And the IP address is next to the line, which represents the part of relationship between this router and this subnet. So router B has actually 3 IP addresses, each for the respective subnet. So this is the IP address of the upper subnet, this of the lower subnet, and this of the right subnet here. So red squares are routers. IP addresses next to these lines are the IP addresses of routers in the respective subnet. And then we have blue rectangles. These are hosts in the respective subnet. And yeah, just do a trivial example. So let's assume that this host wants to communicate with this host. This host on the right is not part of the same subnet as the host on the left. So the communication between these two hosts needs to go through other subnets. So what the router does, what the host, like this is host 1 and this is host 2. What host 1 does, well, it sends the packet that is addressed to host 2, and this packet arrives at router A because the switch in the packet, so this 50.12.230/24 subnet, there's a switch in this subnet connecting all hosts of the respective subnet. And the switch sees that the destination is not something that is local in the subnet. By the way, it does not take a look at the IP address. Switches work at layer 2. So the decision that the destination host is not part of the subnet is made based on the MAC address and not based on the IP address, but the result is the same. A switch detects that the destination is not a member of the current subnet and therefore forwards the packet to the router A, because the router A is like the gateway to other subnets. So the packet arrives at router A, and router A needs to do a routing decision. So router A, well, we see this in the diagram clearly. If the router A is configured correctly and is smart, the router A will forward the packet as a next hop to router B, because router B is a router that is connected to the destination subnet. So router B then detects that the destination is in a network that is connected to router B directly, and then will deliver the packet accordingly. So the route in this minimal example is as drawn in this diagram here. But unfortunately, routers do not have diagrams. Routers need the information in a machine processable form, and these are routing tables. And an actual IPv4 routing table looks like that. We have 3 columns in our routing table. We have the destination, we have the subnet mask, and then we have the next hop. The destination in the subnet mask defines the subnet address, because the destination, you see it, the destination is a network address. So this is not an IP address for a host. This is a network address. And in addition to the network address, we need the information how big the respective subnet is. And this is given by the subnet mask. And the subnet mask is an indicator for the length of the prefix, because subnet mask, the number of ones in the subnet mask is the length of the prefix. And the length of the prefix defines the subnet. So let's take a look at this routing table, especially the first 2 lines. So this is the routing table of router A. And we see in the diagram, router A is part of 2 subnets. Router A is part of the 50/24 subnet, and the router A is also part of the 91/20 subnet. And the router A has these 2 IP addresses respectively. So this 50.12.230.0/24, this translates to a subnet mask of 255.255.255.0, because 24 are ones in the first 24 bits, meaning in the first 3 octets of the subnet mask we have ones. So given a prefix of /20, the subnet mask is 255.255.255.0. And the destination, the value for the destination, is the network address of the subnet. The same with the 91.39.176.0/20. 20 means we have 20 ones in the subnet mask. So the first octet is 0, the second octet is 0, and then 4 zeros are remaining, because here we have 8, here we have 8, means we have 16 in the first 2 octets. And if the prefix is /20, the remaining number of ones is 4, and the rest, the remaining 32 bits, the remainder is 0. So we have 4 bits 1, 4 bits 0 in the third octet, and all zeros in the fourth octet, meaning in dotted decimal notation, this is a value of 240. And this is the same for all like these values. So for example, the 192.0.0.0 and the subnet mask 255.0.0.0. Well, 255 is 8. So we have a prefix of 8 in the subnet, and the next hop will be then this IP address. The last entry here, this is called the default route. This is an interesting route. Why? I will tell you in a bit why this is interesting. But before we talk about the default route, let's see how a router, so a router, again, does not see things. A router has a CPU, and the CPU can process some data. And the approach that a router is doing here is called longest prefix matching. Just the way or the algorithm a router performs in order to find the next hop in the routing table. And the procedure is as follows. We go from top to bottom. So we start at the first row and then go row by row until we hit the bottom of the routing table. And for each entry, so for each row, rows in a routing table are also called routes. So for each route, we calculate this Boolean expression. Destination address. Be careful, this destination address is not this destination value. This is something different. Destination address is exactly the value of this field in the header of the IPv4 datagram. So if a packet arrives at the router takes a look at the destination address and ANDs it together with a subnet mask. The subnet mask is taken from the respective row of the routing table. So the destination IP address is ANDed together with the subnet mask, and then the result is compared with the destination value here. So the result of the AND operation is then compared to the value of the destination column. And if this holds true, we have found what we call a match. So we do a little check mark on the route, and we consider this route as a match. But there can be multiple matches. The question is, if we have ambiguous results, if we have multiple matches, how do we select the correct one? And there the longest prefix comes into play, because we take a look at the prefix of the subnet mask, or the prefix of the route, and the route with the highest or the longest prefix wins and has higher precedence, has higher priority over any other matches. If you ask yourself the question, well, what if we have matches with the same prefix? Then the answer is this should not happen, because then the network configuration is broken. The network engineer has made a boo-boo in the routing table, and a routing algorithm will never construct a routing table in a way that there is a match for an IP address with the same prefix size. So this should not happen, and I guarantee you that this will not happen at the exam. So we exclude this. It's not a possibility. It cannot happen. Okay, let's do an example. Let's do an example with pen and paper, I guess. So the example is this again. So let's take this host. Destination is that host. And this packet, oops, arrives at router A. What happens at router A? Let me switch over real quick. So the destination address, oh, wrong one. The destination address is this one. So let me write this down real quick. 129 0 1 23. And this is our routing table. So what we do first is we take the IP address and AND it together with the subnet mask of our first route that we find, and this is the first row. So the subnet mask is ending it together 255.255.255.0. And the result, you can see this easily because you have either 255s or zeros in the octets. So again, if you see a 255 or a 0 in a subnet, you can do the AND operation quickly, because wherever you have a 255 in an octet, the result of the AND is exactly the value of the first operand, which is 129 and then 0.1. Let me mark that. So these 3 255s mean that the result of the AND operation is the first operand. The last one is 0, so the result is 0. So this is the result of the AND operation. without like doing it in binary, you can directly see this. And the question is, well, is this the destination value? The answer is no. So this is not a match. We can cross this out. Next, the next subnet mask is 255, 255, 240, 0. So let's do this. Again, we have 129, 0, 123, and we AND it together with the subnet mask of the respective route. And this is, you see the 255s are easy. So the result is 129, 0. And actually in an exam, I would stop at this point. Because you see, the result starts with 129, 0. And then you need to compare this value. Does this match with the destination value of the respective route? It cannot, because the respective route starts with 91, 39. So regardless of what the result in the third and fourth octet is, this would not be a match. But anyhow, we will do this for demonstration purposes. So this is 0 again. And the question is, what is the third octet? And the third octet, the 1, this is 1, 2, 3, 4, 5, 6, 7. This is 7 zeros and 1 in binary. And 240, we know this is 4 ones and 4 zeros. And if you AND these together, it's all zeros, right? Because we do not have any bit pair where the two operands are 1, so the result is 0. Meaning that the total result of our AND operation is like this. But again, is this a match? No. Then we take a look at the next row, the subnet mask. Well, 129, 0, 1, 23. This is our destination address. And if you AND the address together with the subnet mask of the third row, you easily see that the result is not the value of the destination. So this is also not a match. But if you take a look at the fourth row and do the same operation, the fourth row is in fact a match. So I will mark this with green. Because if you AND the 129.0123 together with 255.000, then the result is in fact 129.000. So this is a match. And now it gets to the default route. Take a look at the default route. The default route has a subnet mask of all zeros. So it does not matter what the destination address is. The result, if you AND it together with all zeros, is always all zeros, right? So the default route will always match regardless of the value of the destination IP address. Why is this good? Because this is like a fallback mechanism. If a packet does not match with anything before, it always will match to the default route. So it has always a next hop. But question to the round, question to you. What is the prefix of the fourth row? Please put it in chat. It's 8, exactly. So the prefix here is 8. Prefix the number of ones in the subnet address, subnet mask. And the prefix of the last row of the fifth row is 0. According to longest prefix matching, we take the route with the longest prefix, which is this one. So the route that we are taking is this one. So the next hop is the IP address where we forward the packet to at router A with this address. And if we verify this, this works out with our diagram as well. If we here at router A and the destination is this IP address, then we forward the packet to 91.39.176.2, which is router B in the subnet 91.39 and so on. This is the route that we are taking. Yeah, and here again, the example that we just did. Let's train that. There is a task on iLearn that I want you to do. It's routing. And it's actually 3 parts. So let's take a look the first part. So this is the same diagram that we saw on the slides before. And I want you to determine the routing table of router B based on this network layer. So we have seen how this routing table of router A looks like according to this diagram. And now I want you to compile the routing table of router B. You have all the informations here in this subnet. And for that, we don't do breaking rooms. So try to do this on your own, because in the exam you're on the own as well. So what do you have, or how much time do you have in an exam for this? Let me just, I guess it's around 5 to 7 minutes. So I will give you 10 minutes. 10 minutes should be enough in order to solve this. Does anyone have a question before we go into the task? That's a no. So 10 minutes, let's go. Oh, here you see the solution. A routing table always has 3 columns: destination, subnet mask, next hop. You write that down, and then you take a look at the diagram and create an entry for each of the networks that you find in the diagram. So this network is, or these 4 networks, we know these already, but also this is the rest of the internet, so to say. So if this is an extract of the internet and these are 4 internet networks, then this is like the gateway to the rest of the internet. And yeah, I will show the answer real quick. But what you do is you create a entry for each of the networks, right? So this gives you the value for destination and subnet mask. And then you just select the next hop. If the router B is directly or is part of a respective network, you write local to the next hop, because there is then no next hop. You can also write none or leave this, either write none or write local in order to indicate that the router B is directly connected to these subnets. And then, from the perspective of router B, what would be the next hop in order to reach the 50 network? It's the router A, right? And the router A has the IP address 91.39.176.1 in this respective subnet. Be aware that the next hop can only be IP addresses that have a direct subnet connectivity, so a level 2 data link connectivity between each other. So subnet 91 is suitable because router B and router A are both at the same time part of this subnet. So they have like a direct layer 2 connectivity and can forward Ethernet packets. So you can reach this IP address rather easily. And only IP addresses that have layer 2 connectivity are suitable for routing tables. Question, does the order matter? The answer is no, because like the priority of the matches is given by the prefix. So the order does not matter in a routing table. A convention by default, the default route is always the last entry. But for the others, the order does not matter. Oh, yes. For the destination 91.39.170, the subnet mask is wrong. Yeah. Subnet is wrong here. So it should be 255.240. Good that you have spotted this error. Yeah, you're absolutely right. We'll correct this in a bit. But what we do next is we do the task vice versa. So this task type is, I give you a diagram of a network, and you derive a routing table for some router in this diagram. You can do this the other way around as well. I give you a routing table of a router R, which is this one. And now I ask you to create a sketch of the network based on the routing table or based on the informations that you find in the routing table for router R. And please replace the parts of IP addresses that cannot be determined with the information that you have, because a routing table has not all the informations of all the networks, it just has the information of like the proximity of a router. And you cannot determine some parts of IP addresses. And in that case, you use a question mark. But now I want you to draw a diagram based on the information of router R with the same like syntax or structure element that you find here. So subnets are clouds and routers are squares, and hosts are, there are no hosts in routing tables. But you express part of relationships with a line between a router and a subnet and so on. Note that this routing table has no relation to this diagram. So these are completely independent tasks. How many routes do we have here? 1, 2, 3, 4, 5, 6. In an exam, I would give you 2 minutes for each route. So you have 12 minutes in an exam. Maybe a little less, 10 minutes for an exam. Anyhow, I will give you 15 minutes. Everyone, put out your pen and paper and draw a sketch of this network. Any questions before we go into the task? Then 15 minutes, let's go. Oh, welcome back. Take a look at this nice diagram that I drew before. So the routing table R is sketched this way. There is this only way. There are no alternatives. And I will explain how I created this diagram. Um, well, I will, before I do that, I will take 2 minutes in order for you to compare like your sketch with this sketch and maybe do some notes. Like before I switch back and forth the table and then um, explain what I did. Hey, oh, let's take a look at the, oh, this is the wrong one. Let's take a look at the table. Table. Here. This is the table. And what you do first is you take a close look at the table. And you see two things immediately. There are two networks here, route 4 and route 5, which are local to the router. Keep that in mind. And we have two networks that start with 32. And what you need to spot there is that the 3220 network with the /16 prefix, 16 because we have two 255s here. This is /8, this is /16. That this network here, the second one, is in fact a subnet of the first one. This is what you need to spot, because the range of the IP addresses lies in the range of the of this network here. So the 3220 is a subnet of the 32. And then the strategy to draw this is you start with the local ones, because these are directly connected to the router R. I did exactly this. So I start, or you should start with the router R, and then draw the respective networks directly next to each other. So we have the 207.10.100.0/24, and we have the 128.100/16. The 24 and the 16 are derived from the subnet mask. So this 255.255.255.0, this is 24 ones. So the prefix is /24. 255.255.0.0 has 16 ones. So the prefix is 16. Then the IP address of the router in the respective subnet. This is a little tricky because what we know is, if we consider the /16 network here, we know that the prefix is 16, the network portion of addresses inside is 16, and the host portion is 16. This gives us the information that the IP address of the router in this subnet here needs to start with the 16 bits of the network portion. And this is 128.1. And for the host portions, we don't know. I mean, there is a convention that the router typically gets the first usable host in a network, which would be 128.101. But this is not written or carved into stone. Some people, in fact, like putting routers at any arbitrary address in a subnet for security reasons. Security through obfuscation is the key word here. But in essence, we don't know what the router R or the IP address of the router R is in this subnet 128. The same applies for 207.10.100/24. We know the network portion is 24 bits long, meaning that the IP address of the router R in the respective subnets needs to start with the 24 bits of the network portion of this subnet, which is 207.10.100. And the remaining 8 bits, the remaining octet, is unknown. And this covers these two lines in our routing table. Next, let's cover these two, the 32 and the 3220. As said before, you need to see that the one is a subnet of the other. So the 3220/16 is a subnet of 32.0.0.0/8. And there are two IP addresses given for the next hop for these networks. So from router R, we can reach the 32.20.0.0/16 using a next hop of 207.10.109. 207.10.109, we see this from the IP address, is a part of the 207.10.100.0/24 network. So it needs to pass like this subnet. And the IP address of this router, again, we don't know all parts of the IP addresses, but we know the IP address needs to be in the 32.20.0.0/16 network. So the host portion are the latter 2 bits, and the network portion are the former 2 bits. So the IP address needs to start with 3220, and the remaining 2 octets are unknown. For the 32.0.0/8, the same method apply. We know our next hop from router R to reach this network is this IP address. So the IP address of the router that is the gateway to the 32/8 IP network is this IP address 207.10.108. And the router's IP address in the 32 network is unknown except for the network portion, which is 32 unknown. And with the same method, we add the 48. We have these two. The remaining route, or the two remaining routes, are the 42, the 48/8 and the default route. The 48/8 is represented here. We reach the 48/8 network through an IP address 128.1010, which is part of this network, which is directly connected to router R. So we know this IP address, but we only know the first byte of the IP address of this router in the 48/8 network. And then finally, we have the default route, which goes over 128.1011. And through this router, we can reach the rest of the internet / the rest of the network. Any questions on this? Then let's do part 3. Part 3 is easy. We do this together before we go into the break. Let me make this a little bit smaller such that you have the IP addresses and the routing table in one page. And you write into chat what is the next hop if router R sees an IP packet with a destination IP value of this IP address. So what would be the next hop when router R sees this IP address? Write into chat. Yes, correct. It's 128.1010. What's the next hop for 3220.1855? Exactly. 27, 10, 109. What's the next hop for this one? 3221.1956. Exactly. So the difference between these two is the 3220 is part of this network where the next hop is 207.10.109 and 3221.1956. It's part of this network here, right? So they are close in the IP address space, but the second bullet is part of the smaller one, 3220, and the 3221 is part of the bigger network. So the next hop is 207.10.108. What's the next hop of 207.10.100.1.1? It's exactly. It's the default route. The default route. So the next hop is 128.1.0.11 because this IP address, the 207.10.101.1, it's not in this subnet, it's not in that subnet, it's not in this one, it's not in this one. Because this one, this network, it's a /24 network. So the host portion is the last octet, and the third octet different. So this goes to the default route because it's also not part of this network. The default route is 128.1.0.11. And last but not least, what is the next hop of this IP address? The last one. Exactly, it's local, meaning there is no next hop because the router R is part of the 207.10.100.0/24 subnet. So the router R can directly deliver the IP packet to this IP address. Okay, perfect. Well, let's do a break of 15 minutes. Are there any questions? I show the answer of part 2 is. It's here.
Excuse me, I have a question about the mock exam. So I saw that you posted it on iLearn. Is that the final version of the mock exam, or you're gonna make it different somehow? Because you said that you're gonna post it 2 weeks in advance, and now it's like a bit early. That's why I'm curious.
No. It will be the final. mock exam, but it's a mock exam, right? So expect different questions in the actual exam.
Yeah, of course, but just to make sure. Thank you.
Another question, can I explain what parts are not coming in the exam? There is an exclusion list of topics that we have not covered in classes and were not covered by any other means. And this is the exclusion list. So from the operating system parts, we excluded threads. We excluded the ext4 case studies. From the networks part, we exclude CRC. This would be the next topic. We will exclude ICMP. And we also will exclude DNS. For the last question. What is the next hop for this IP address? I will write this in chat. The answer is the default route 128.1.0.11. Okay, let's do a break. Talk to you in 15 minutes. Oh, welcome back, everyone. From the break, second half of our lecture today, most of the parts of the network protocols discussions is in the network layer. In the transport layer, we focus on what's important. This will be the TCP protocol, by the way. But before we talk protocols, let's see what the transport layer is all about. Because the transport layer is important for people who program networking services. And you as artificial intelligence students will likely to program things based on a network, because machine learning and model training and machine learning algorithms are very computational heavy tasks. So you will do a lot of number crunching. And if you want to train models where the compute resources of your local machine are not enough, you need to spread out and you need to distribute your calculation. And guess what? What are you using in order to spread out the calculations on multiple machines? You will use the network. And as a programmer, for networking applications, you use the transport layer. This is also the interface between the operating system and programs that you write. So the application layer is in user space, and the transport layer is part of the operating system, so it operates in kernel space. The interface in between is what we call a socket. A socket is a structure that the operating system provides to programmers in order to have like an endpoint for network communication. Because sockets exist on both sides of the networking application. So assuming on host 1, you have a process, and on host 2, you have a process, and these two processes are communicating with each other. So both of these processes use a socket provided by the operating system. And this socket, it's like a funnel. You pour in data from one side, and this data spreads out at the other side. If you write to this socket here, the operating system takes care that the data comes out exactly here. This is realized using a transport entity. Typically, this is the TCP protocol, the most dominant protocol in TCP/IP networking, so in the common networking stack that we know. And this realizes a virtual connection between two applications. And this is, again, this is part of the operating system. So you request this service from the operating system and you get it, and you don't see what's behind the curtain, because the transport layer talks to the network layer. The network layer, routing decisions are made and such. Yeah, we know this already. So as a programmer, you use sockets, an endpoint in software for sending or receiving a data. You can imagine this as a data funnel. The part of the operating system that provides you as a programmer this service is called the socket API. It's a logical link between these two processes. You identify these processes by the port numbers. We have stumbled over these port numbers already. These are 16-bit port numbers. For example, HTTP protocol, port 80. HTTPS uses port 443. DNS uses, what is DNS port? 53? Yeah. File transfer protocol, port 21, and so on and so forth. So if you program a networked application, you can define this port. You can say your application, if this is a server application, so it provides services to clients, then you can define the port that your application is listening on. And a client then uses this port to identify your application on the server's host. So you use the IP address in order to identify the host. And as one host can host multiple applications, you distinguish these applications using port numbers. and you need the client needs a port number in order to identify the correct application at the target host. This is called socket programming. And typically, well, you can do socket programming in operating system and networks, but as this module is already stuffed with a lot of topics, because we have the operating system parts, we have the network parts, I only do socket programming in this format if we have really much time left. But as I'm sick all the time, unfortunately, we don't have much time left, so we skip socket programming as well. But sometimes you do this in programming too. Which professor do you have in programming too next semester? I guess it's Florian Wahl. Maybe Florian Wahl will do socket programming as part of programming. So the way how you program software in order to consume sockets, meaning connecting to applications over a network. There are two very, one protocol is more dominant than the other one. So we have two famous protocols in the transport layer, UDP and TCP, whereas UDP is quite simple in a sense that it's the simplest possible transport protocol. It does not have any quirks or features. It is unreliable because it does not have a way how to establish reliability. It does not use the concept of a connection. So it's connectionless, it's unreliable. So there is no context besides question and answers. Because of the simplicity, because of the simplicity, it gains in performance, because if you do not care about reliability, or if you do not need to establish a connection, this is then more performant. And sometimes in some use cases, it's not the end of the world if you have higher packet loss, but you need the performance in these use cases, then UDP might be a good protocol. But as we advance in technology, we advance in available bandwidth, we advance in network cards, we advance in computational power, and all this like resources, computational resources, these shift like the ratio of applications using UDP and TCP more towards TCP, because we simply have the computational power in order to always use reliable and connection-oriented. But applications where UDP is still employed are voice over IP, DNS uses uses UDP, and sometimes media streaming. But Netflix as well as Amazon Prime switched from UDP to TCP recently, let's say in the recent years. Today, if you watch a Netflix stream, it's TCP. Just a quick look at the UDP header. There is not much going on. It's just the bare minimum that you need. You need service addressing realized in 16-bit port numbers. So you have the source port, the destination port, you have the length of the payload, and you have the checksum. Well, everything you need, basically you don't need the checksum, but we talked about checksums before. So every layer has some checksum because why not? And the source port, sender port, destination port, the receiver's port. Length is the number of bytes of the transport entity, so the UDP header plus the UDP payload. And the checksum, optional. If it's not used, and typically it's not used, it's all zeros. Here you have some examples of applications that use UDP as transport layer protocol. We have the network time protocol, DNS, DHCP, RTSP, and some like edge use case, the media gateway control protocol, but to be honest, not really used in practice. So let's focus what's important, or what's more important. UDP is important as well, but more important is TCP. TCP bases on the work of Cerf and Kahn, which was cited in this class quite often. So this famous paper of 1974, you need to imagine 1974, so mid-17, these two people invented the internet. In a sense, they invented networking. Tim Berners-Lee in the 90s invented then the internet and invented the World Wide Web. But Tim Berners-Lee in the 90s could not achieve build up the internet that we know it today if there was not the work of Cerf and Kahn before. So in this 1974 paper, there was a early discussion on how an IP protocol and a TCP protocol can look like. This was refined and then experimented in the lab. And eventually it was formally defined in 1981, so early 80s. TCP is reliable, TCP is connection-oriented, and TCP is popular. This reliability and connection orientation requires some additional aspects of the protocol. Also, it requires some compute and networking resources. But nowadays we have these resources. So the question that you ask yourself if you design a new network application is, do you really need the maximum performance that is just possible? Then you choose UDP. But if you say, well, I can invest these resources for having a reliable and connection-oriented protocol, then you opt for TCP. The World Wide Web, the protocol where the World Wide Web is based on, is called HTTP, Hypertext Transfer Protocol. Terminal sessions with SSH and file transfer with FTP are examples for TCP. So let's see. Now let's focus on two aspects of the TCP protocol. How can we establish reliability? And how can we create and terminate a connection? For that, let's take a look at the TCP header. It's complex as the IP header, but there are a lot of fields that are not in scope of our discussion, and some fields are not used anymore as well. So what we need in any case is source port and destination port. So these two, we need these in any case for service port addressing. And then we have these two rows here. These are important. The sequence number is the mechanism how we can establish reliability. In fact, both the sequence number and acknowledgement number are used for reliability. Because when you think about reliability, what does that mean? Reliability means that we receive all packets in order, and the order is defined by the sequence number. And the second aspect of reliability is that we must not lose packets due to packet loss, or if a packet is compromised, like a bit flip is in there somewhere. Or lost or damaged packets, we need to care about this. And this is done by acknowledgement numbers. So the sequence number is not a counter. So it's not packet 1, 2, 3, 4, 5, and 6. The value for the sequence number is the amount of bytes that was sent by the sender. And if a packet, let's say, is 1 kilobyte of size, then you initialize the sequence number randomly. So it does not start at 0. It starts at a random number x. And the sequence number, well, it starts at x. The first packet has the sequence number x. And the second number is then x plus the amount of bytes that was sent before. So, for example, X plus a kilobyte. And the third packet is then X plus 2 kilobytes, 3 kilobytes, and so on and so forth. So the sequence number is not a counter. It's the number of bytes that was sent by the sender starting at a random offset. The acknowledgement number is the same. It's not a counter. It's the amount of data that was received by the receiver starting at a random number y. These two starting points, x and y, are different from each other. The sender defines x and the receiver defines y. Because the idea of the TCP protocol is that the receiver gets back with a feedback, with an acknowledgement that a packet was received without errors, uncompromised, in full. In essence, whenever you send a packet, you get an acknowledgement back if the packet was delivered successfully. If the packet was not successfully delivered, you do not get an acknowledgement number. So the sequence number for ordering and the acknowledgement number, it's like a receipt that the sender gets from the receiver that a certain amount of bytes is already received in full. What do we have next? We have a data offset. We need the data offset because we have options here already. But options, it's not used in practice the same as in IPv4. The protocol defines variable options, not used in practice. Urgent pointer, oops, let's cross it out. Also defined in the standardization, not used in practice. Checksum, defined in the protocol, not really used in practice. And then we have a lot of flags here. We have fin, syn, reset, push, acknowledge, urgent, ECE, CBR. These are in fact used in practice, but we won't talk about them today because we only focus on the parts of the TCP standard that are of interest for us. And this is how can we establish the order and how can we create or establish and terminate connections. So the important fields for our discussion: source port, destination port, sequence number, acknowledgement number. The window size will hopefully clarify at the end of our lecture today. Yeah, well, in the data offset, I mean, it's used, but it's always 20 bytes. Because without options, the header, the size of the header is always 20 bytes. The data offset is an information that defines the border between where does the header end and where does the payload start. And if you do not have variable options, this is always 20 bytes. The fields, again, explained on the slide that you can recite this at home in preparation for the exam. A question from Lal Amar, do we need to remember the port numbers? The answer is no. You don't remember them. You don't need to remember any port numbers. The flags in the TCP header that are of interest for us, fin, back. But you need to know that these are flags in the TCP header. Flags, by the way, meaning, going back real quick, a flag meaning it's one bit located as you see it here. And if this bit is 1, then the flag is activated. If the bit is 0, then the flag is deactivated. So a flag has two states, active and non-active. And if the bit here is set to 1, then this flag is enabled. Otherwise, it's disabled. And we need these flags for the way how we establish and terminate connections. So to answer this question, how can we create a TCP connection? We need to talk about the three-way handshake. And this works as follows. What you see here, it's in fact a standardized diagram. This is an UML sequence diagram. But without going into details on how UML works, this diagram shows the timeline in exchanging messages between two hosts. So we have host 1 and host 2 here, and time flows from top to bottom. And the arrows that you see here, these are messages. So host 1 sends a message to host 2 answers with a message, and then finally, because it's a three-way handshake, the first host sends a message again to host 2. These three messages, so the message exchange in the three-way handshake, establish a connection. And this is done with the SYN, ACK, and the SYN and the ACK flags. So in order to establish a connection, or let's say host 1 is the initiator and host 1 wants to establish a connection to host 2. Then host 1 sends a TCP packet with the SYN flag enabled to host 2 and randomly defines a sequence number. A sequence number X can be anywhere in the 16-bit address space. And with this message, with the SYN and the sequence number X, it tells host 2, well, here I am, host 1, I want to create a TCP connection with you, and I use sequence numbers that are starting with X. Host 2 acknowledges this by sending a TCP packet back and says, well, I accept that I want to establish a connection by making the SYN flag on, so setting the SYN flag, and at the same time acknowledging the SYN that you got before, so enabling the ACK flag as well. And in the acknowledgement number field, you put a value of X plus 1. This indicates that host 2 acknowledges the SYN request with the sequence number X. And at the same time, host 2 sets a sequence number of Y. And with these two messages, the two hosts agree on respective starting points for their sequence number. So host 1 tells host 2, look, I want to establish a connection and I start with X. And host 2 says, well, fine by me, let's establish connection, but I will start my sequence numbers at Y. There are IT security reasons why these two sequence numbers are random. There are attacks, which is called TCP session hijacking, not topic of today, but there are IT security attacks that randomly guess the sequence number and try to hijack a TCP connection. And in order to avoid that, host 2 and host 1 randomly choose the sequence number and tell these sequence numbers the other communication partner. So SYN and ACK comes back and host 1 then acknowledges that host 1 will respect packets that come back with a sequence number of Y, with setting the sequence number, or the last packet, the third packet of the three-way handshake is then an ACK with sequence number X plus 1 and an acknowledgement of Y plus 1. And then the TCP connection is established and the data exchange using TCP packets can go on, and host 1 and host 2 exchange data. This is the way how we create and establish a connection. The four-way handshake, on the other hand, is the way how we terminate connection. And this is it's not super clear in this diagram, but this is a two-phase method. this four-way handshake, I mean, it's called four-way handshake, but the better name would be a 2+2 handshake, because you have a virtual separation between here. Because let's assume host 1 decides to terminate the connection. Instead of sending a fin with a sequence number, instead of sending a SYN, it sends a fin. Fin means finished, finishing, or terminating the connection with the current sequence number M. So this is, it depends on how much data was exchanged, but this is like the follow-up sequence number of the data exchange before. Let's call this its sequence number M. Host 2 gets this, this request to terminate the connection and then acknowledges that host 2 has in fact received the fin request and sends back an acknowledgement for this fin, meaning it sets sequence number N is the next in the sequence, and it acknowledges that it got the packet with a sequence number M by sending an acknowledgement. And an acknowledgement is a TCP packet where the acknowledgement flag is set to 1. And if the acknowledge flag is set to 1, we find the respective acknowledgement number in the field for the acknowledgement number, where the value of M+1 is. And this gets back to host 1. So host 1 detects, my fin packet was arrived successfully, nice. And then the waiting time starts, because host 2 then knows, well, host 1 wants to terminate, and maybe there is some tasks that are left over to do, like housekeeping, deallocating memory structures, whatever host 2 needs to do before host 2 is actually ready to terminate the connection. If this point in time is arrived, host 2 will then contact host 1 again and says, well, I'm ready now. And host 2 sends a fin plus an ACK to host 1 with a sequence number of O, and so O is a random number, and ACK with M+1. M+1 meaning that this previous ACK and the next ACK will fit together. So this is a follow-up message to the one before. And host 1 then acknowledges the delivery of the fin request of host 2 to host 1. Again, because there's a question chat to explain it again. I will remove the virtual line real quick. Basically, these two belong together. At one point in time, host 1 decides to terminate the connection with host 2. So host 1 sends a fin to host 2. And this fin is acknowledged by host 2. Remember, we have a reliable protocol. Reliability means that we need to acknowledge packets that we have received, because otherwise host 1 does not know or has no guarantee that the fin request actually was delivered to host 2, because there's always the possibility that this fin packet is either damaged or lost, because we have packet loss. It's there. And this fin packet can be lost. So in order for host 1 to have the guarantee that the fin packet has been received at host 2, it waits for an acknowledgement that the fin packet was arrived or was delivered in full. And this is this packet here. It's the ACK, where the sequence numbers match. So the ACK, so the acknowledgement number, needs to fit to the sequence number of the fin packet. And then At this point in time, like here, at this point in time, host 2 knows, well, host 1 wants to terminate the connection, and host 2 has acknowledged the FIN request, but the connection is not terminated yet because there maybe it depends on the use case, but maybe host 2 needs to do something before the actual connection can be terminated, like housekeeping, deallocating memory structures, doing basically anything that host 2 requires or needs to do before the connection is actually terminated, like doing some leftover tasks. So the connection is not terminated immediately, but host 1 waits until host 2 is ready. And host 2 informs host 1 that host 2 is in fact ready by this FIN plus act. So when host 2 sends back to host 1 also a FIN packet with acknowledging as well, and the acknowledgement numbers are the same, then host 1 knows, fine, host 2 is also ready to terminate the connection. Then it's acknowledged again, because every packet needs to be acknowledged. And as this FIN comes from host 2 to host 1 needs to acknowledge the receipt of this FIN packet and gets with an acknowledgement back. This time here in between, this is called the close waiting time. Close waiting time. Wait. I'm bad at writing with my mouse. Any questions? Let's proceed. The technical term for packets requiring an acknowledgement is called ARQ. And this is a method for retransmitting packets that are not acknowledged by an acknowledgement packet. And this works with a timeout. So when a sender sends a packet, it triggers a timeout, let's say 150 milliseconds. And if in this 150 milliseconds, if there is no acknowledgement getting back from receiver to the sender, then the sender assumes that the packet was lost and automatically retransmitted. Automatic repeat requests based on a timeout. And if an acknowledgement gets back, then the sender knows, well, this packet was acknowledged, nice, I'm sending the next one. And waiting for this acknowledgement is called stop and wait. I have a diagram for that. So here, stop and wait. Let's focus on the left diagram before we take a look at the right one. So as an example, host 1 sends a packet with a sequence number to host 2. The packet is 1460 bytes, which is a realistic value. And then the host 2 sends back an acknowledgement for exactly this sequence number X. And then once the acknowledgement has arrived at host 1, you send the next packet and you wait for the acknowledgement. Then you send the next, then you wait for the acknowledgement. Yeah? Stop and wait. You send and stop until the acknowledgement gets back from the receiver. This is called stop and wait. And you see it in the diagram directly that this is largely inefficient. I mean, it's reliable, right? So reliability is one of the main aspects of the TCP protocol. So we need these acknowledgements, but waiting for the acknowledgements is inefficient. So then the next idea is, let's do pipelining. So let's send packets and do not wait for the acknowledgements, and do this in an asynchronous manner, right? As you see it here. So in this case, pipelining, host 1 sends packets to host 2, but does not wait for the acknowledgements before sending the next packet. This is in fact efficient, and this gets the most performance in a sense that you can send a larger volume of data in a smaller amount of time. And you clearly get a better performance in pipelining. So the data rates, like the bits per second that you can push through the network, is higher in pipelining, significantly higher in pipelining than in stop and wait. But the question is, can I do pipelining, or what do I do when there is packet loss? Because if I just send no matter what, then these acknowledgements are somehow irrelevant, question mark? And the answer is yes and no. If we do pipelining with no upper limit, then we have a problem. Because it does not take packet loss into consideration. We need some kind of a middle way where we say we do pipelining because pipelining is efficient, but we limit the degree of the pipeline to a upper limit. And what I try to describe it in like fuzzy words, there's a very strict process for this pipelining approach in the TCP protocol, and this is called the sliding window protocol. Both sender and receiver have queues, and these queues have slots for TCP packets. And this queue is a number of packets long. So for example, we have 10 packets or a 10 packet queue at the sender side and a 10 packet queue in the receiver side. And this queue respects the order. So this queue is in fact ordered in a sense that it's a sequence. Right? So packet 1 is at front, and then packet 2, packet 3, packet 4, packet 5, packet 6, packet 7, and so on. And the same for the receiver. The receiver has a receiving queue, and the order in this receiving queue matters. Receiving queue for packet 1, packet 2, packet 3, packet 4, packet 5, and so on. And the sender does the following. The sender sends as long there is space in the sending queue. So assuming, or let's go one slide. Yeah, one slide next. Here you see a diagram how this works. So we have a sending queue, and this sending queue has a maximum size. How many is this in this example? 1, 2, 3, 4, 5, 6, 7, 8. So here in this example, the sending queue or the sending window, we call this a sending window, is 8 packets big, and the sender sends packets that are inside this sending window. So in this case, the sending window lies here, and this is, well, this is packet 1, this is packet 2, this is packet 3, this is packet 4, 5, 6, 7, 8, 9. In this example, the sender is in the process of sending packet 10, And if packet 10 is sent, it continues with packet 11 and packet 12. 11, 12. But after packet 12, the sender stops with sending because the sender only sends packets that are in the sending window. The sender does not send any packets outside the sending window. And the sending window over time moves from left to right. Because otherwise we would stop at, in this example, 12 and never send packet 13. The sending window moves to the right. But what triggers a move or a shift to the right? The answer is acknowledgements. Second. So let's take a look at this diagram. It's still the sender's perspective. This is the sending window. And then an acknowledgement arrives for this packet. What is this packet? 1, 2, 3, 4, 5, 6, 7. And then at some time, an acknowledgement for this packet, packet 7, arrives. And the idea of the sliding window is whenever the sender gets an acknowledgement for a packet, and you can determine this by the sequence and acknowledgement numbers. So when the sender gets this acknowledgement for 7, the sender knows that all packets to 7, including 7, have been received at the receiver's end. And then the sliding window shifts as many positions to the right as the last acknowledgement received. So this is this parameter. LAR means last acknowledgement received. Previously, this packet was the last acknowledged one, and now it's this one. And the sending window then shifts to the right and makes more room for the sender to send. And if this process happens quick enough, the sending window always has some room for the sender to send new packets. Right? So HSS is highest sequence number sent. So this arrow means the sender is just in the process of sending this packet, because the sending process also takes time. And so it takes time for the network card to send out the packets to the transmission medium. So if the sender is currently sending this packet and an acknowledgement for this arrives, then we shift the sliding window 3 positions to the right, and the sending window has more room, so the sender can continue sending. So this happens at the sender side. At the receiver side, we have also a receiving window, but we know that, again, I'm opening my my terminal here, and I'm pinging the Technical University of I need to connect to my home server and do a trace route. We know, here you have the example again, that packets, they jump from host to host or from router to router. What you see here, these are the routers, the hops that the packet takes, like 10 in total. Let's subtract 1 because the first one is my router at home, my Fritzbox. It takes 10 hops from sender to receiver when we doing internet traffic. And the implications are that packets may arrive out of order. So one packet overtakes the other packet, so to say. And this situation is illustrated in this diagram. So this is the receiver side. The receiver receives the packets out of order. So for example, 1, 2, 3, 4, 5. This is packet 6. This is packet 7. And the rule at the receiver is whenever there is a complete sequence in the receiving window, only then an acknowledgement is sent back to the sender. Look at this example. In this example, we do not have a sequence, a complete sequence in the receiving window because 5 is missing. So we are missing packet 5. And therefore, we do not have a sequence in the receiving window. And the receiver waits for packet 5 to arrive. Maybe it required a detour. In this slide, you see the situation where packet 5 arrives. Now, we have a sequence in the receiving window. And the sequence is up to 7, because this is packet 7, right? And the arrival of packet 5 makes the sequence, the in-order sequence of the packets full up to packet 7. And then the receiver sends back an acknowledgement, not for packet 5, although packet 5 arrives at the arrives last. An acknowledgement is sent for package 7 because the receiver always acknowledges the highest packet number, the highest sequence number that has arrived at the receiver. What gets back to the sender is an acknowledgement for packet 7. And when this is the case, the receiving window then shifts as many positions to the right until we hit the last acknowledgement sent, such that we have room in the receiving window again. This is efficient. To recap it, the sender retransmit a packet if a pre-configured timeout has elapsed. So maybe a packet is lost, right? So maybe packet 5 is lost. Then packet 5 never arrives here. Then the sender will never send an acknowledgement back because it still waits for packet 5. Then a timeout triggers at the sender and the packet is sent again. Or the sequence number is greater than the last acknowledgement received. The receiver accept packets basically if the packet is inside this receiving window. If a packet arrives that has a sequence number that is smaller than LAS, then it's discarded. If we receive a packet that is outside the receiving window with a higher number than HSA, then we also discard it. This sliding windows, in practice, this happens really fast. This happens like shifts to the right, both on sender and receiver side. This happens in like milliseconds. And this, the size of the window, this is exactly the degree of pipelining in this diagram. The number of packets that a sender can send without getting an acknowledgement back is limited by the sending window size. But if the acknowledgements come back fast enough, because there is low packet loss, then the receiving or the sending window shifts to the right. And on the other hand, if the packets arrive mostly in order and mostly uncompromised, then also the receiving window shifts to the right. Only if the transmission medium is suboptimal, like you have a Wi-Fi transmission medium and a microwave in between, then you have a large ratio of packet loss. But if you don't have a large ratio of packet loss, for example, if you have a copper wire connection, where you have a packet loss less than 1%, then the windows shift fast enough in order for this pipelining working so good that the sender can continuously send and never has to wait for any acknowledgements. This is the goal. The goal is to send the packets at full speed to reach the full bandwidth of the transmission medium. And this works if we have a large enough degree of pipelining and the acknowledgements can come back quick enough. This sliding window, let's train this. It's the last thing that we do today. Before we go into the task, there's a question. You need to read the question real quick. Since we have to wait for a sequence to move the last acknowledgement, it's very time consuming. Is it possible to break the big block into smaller blocks and do it group wise? Interesting idea. It will increase the number of acknowledgements, but it will reduce the time. The idea is nice, like breaking a big problem into smaller groups, and maybe we can do a more efficient approach on smaller groups. But unfortunately, this will not have a benefit, because still, if you do groupings, like let me have this is a group, and this is a group, and this is a group. Still, if this packet is never receiving, then the receiver needs to wait for this packet to be received in order to guarantee, like the TCP protocol is always about guarantees. And you need to wait at some point for this packet to arrive in order to process other packets as well. And for that, you have a bottleneck on this one. And regardless on how efficient you process other packets, you still need to wait for this one. So it won't tackle your problem. The bottleneck this packet. In practice, these windows are rather big. I guess 100 to 200 is a realistic value for these queues. But I cannot illustrate the 100 packets here, because then the diagrams would be small. So let's take a look at the task. Because the task is it's the most complex task that we will discuss in this lecture. And we start with a network configuration. Let's say we have a bandwidth of 10 megabits per second. It's a small, it's a slow internet connection. Propagation delay is 50 milliseconds. What is meant by propagation delay means is this is a delay. It's the time that an electrical signal requires from one host to another. This requires some times, and it's longer the longer the distance between two hosts is. And let's say the signal requires 50 milliseconds from one host to another host. The size of a packet should be 32 kilobytes. And the size of an acknowledgement package, we don't care about that. We say the size of these packets is negligible. I cannot pronounce this word, but we don't care about this ACK. We don't care about the size of the ACK packet. And then the transport shall be based on TCP using the sliding window protocol with the following properties. We have a timeout of 150 milliseconds. The sender window shall be 4. The receiver window shall be 2. Minimal example, such that we see what's actually going on. And then there's a twist. Every third packet gets lost. But ACK messages do not get lost at all. And our task is, I will start it such that you get a feeling on how this task needs to be done. We need to simulate the transmission of 192 kilobytes with pen and paper using the template that's attached there. So there's a template attached. I will open it up. And this is a worksheet where you have steps from time 0 to time 300. And this is the situation at the sender. So these are the blocks of the messages. Because we need to send 192 kilobytes, which is exactly six packets. And then we describe what the sender is doing and what the receiver is doing. And our job is to simulate, according to the sliding window protocol, how the sending and receiving windows are moving and what happens in this scenario. And spoiler alert, this scenario is not constructed towards a realistic scenario because in reality, we do not have much packet loss. So a packet loss of every third packet is lost is a packet loss of 33%. It's incredibly high. But the example here is constructed in a way where everything that can go wrong goes wrong, such that you see what happens according to the sliding window protocol. So it's constructed for demonstration purposes, and it does not have the example is not constructed in a way to show reality. Keep this in mind. And then we should use the following abbreviations. Well, you see this here. When a packet is sent but not acknowledged yet, and a timeout occurs at 175 milliseconds, then we write this value to the sender. Timeouts only can occur at the sender side. That this packet 1, timeouts at a time of 175. A means package is acknowledged, and R means packet is received but not acknowledged. So before we go into, I will start with this task in order to see how this is done, and your job is to finish it at home. And for that, let me switch to my. Does this move? Yes. So I have it on my tablet here, and I will explain what is going on. The first thing that we need to know is how long does it take for 32 kilobytes to be sent on a 10 megabit per second bandwidth. So this is the first question, and this is a simple calculation. Where are my notes? Where are my notes for today? Oh, it's here. So we have 32 kilobytes, and we have a bandwidth of 10 megabits per second. And the time that we need in order to send 32 kilobytes over a 10 megabit per second network connection. This is the transfer time. I will abbreviate it with TT, transfer time. It's just a ratio, just a fraction, 32 kilobytes over 10 megabits per second. And this is 25 milliseconds. Okay, you can put this into the calculator. For time reasons, I won't do the calculation in detail, but you have to believe me, this is 25 milliseconds. So what does this mean? This means that the whole network stack at the sender requires 25 milliseconds for assembling the packet, going through the transport layer, going through the network layer, going through the data link layer, going through the physical layer, and sending, or the time of sending the first bit to sending the last bit is exactly 25 milliseconds. So at time T1, T0, which is 0 milliseconds, the first bit of the message is put onto the transmission medium. And at T1, which is 25 milliseconds, the last bit of the packet has left the network card of the sending host. So this is what these 25 milliseconds are. When we have a bandwidth of 10 megabits per second and we have a packet size of 32 kilobytes, then we require 25 milliseconds for the sending process. So the time difference between the first bit and the last bit of the packet is exactly 25 milliseconds. And once these 25 milliseconds are over, this is host 1 and host 2, if this 25 milliseconds are over, then the packet is on its way. But the packet has to travel, let's say, 2,000 kilometers. And there the propagation delay comes into play. The time the packet requires to travel from H1 to H2 is 50 milliseconds. It's the parameter that we have given here. So the propagation delay, 50 milliseconds. So once the packet is sent, or the packet leaves the sender, it requires 50 milliseconds to be received. Like host 1, in this example, host 1 requires 25 milliseconds to put packet onto the 10 megabit per second line, and then the travel time is 50 milliseconds. This needs to be clear, because then with this information we can start. Let's focus on the first row. Initially, we start transmitting the first packet, right? So start transmission of packet 1. This happens at time 0. At time 0, the sender begins with sending the first bit of the first packet. There is nothing on the receiver's end because the receiver did not receive anything. And then the next row is time 25. And there, packet 1 is on its way. And we start with transmitting packet 2. Start transmitting packet 2. So this is what we do at the sender end. But when packet 1 is on its way and it has just left the sender, it requires 50 milliseconds, because this is our travel time, our propagation delay, travel time. It requires 50 milliseconds to travel to the receiver. So the receiving time is the time t 75. So now at time 25, we are done sending. Now the travel time of 50 milliseconds follows. So the arrival time is 75 of packet 1. At the same time, P1 is on its way. The sender has room. So the sending window is exactly of size 4. So we have room in our sending window, so we start sending packet 2. And as we have a timeout of 150 milliseconds, this first packet will time out at a time of 175. At the receiver's end, we have nothing. And in this fashion, we continue. At time 50, P2 is on its way. The arrival is 100. And we start transmitting packet 3. On the receiver's end, well, like if the first bit is sent at time 0, then the first bit of packet 1 is just arriving at the receiver. Not the full packet, but the first bit of the packet arrives at the receiver. So the first packet starts to receive, but it's not received in full. But the first bit has traveled like 50 milliseconds already. Okay, next. Oh, not next. It's 175, and this timeout is 200. And the window is still the first 4 packets. Perfect. So what happens at time 75? This is our sending window. It's 200. Packet 3 has a timeout of 255 because packet 3 is on its way, but remember, this is the twist, every third packet gets lost. Oops. The packet 3 is on its way, but it gets lost. And we start transmitting packet 4. Because we still have room in our sending window. This happens at the sender. The receiver. Let's zoom in. Yeah. So at the receiver, P1 is received and P2 starts to receive. And now the following happens, right? So this is our receiving window. The first packet arrives. And the packet is put here. Right? And as it is a sequence in the receiving window, a single packet is still a sequence, right? So there is no hole in the receiving window. So there is no hole in the receiving window, meaning that we acknowledge this. So the receiver gets packet 1, it's in sequence, it's in order. I need some space. Packet 2 starts to receive and pack 1 gets back. And the receiving window shifts by 1 position to the right. Question, what does 200 mean? This is the timeout when the packet or the timeout of packet 2 triggers at a time 200. 200 because it is on its way, so it leaves the sender at the time 50. If the timeout value is 150, the timeout time is 200. Finally, let's do time 100 again. No, not again. Let's do time 100. So next, and this is our receiving window. This is our this is sending window and receiving window. This acknowledgement 1 gets back the time it is received, because it takes 50 milliseconds. This is our travel time, right? So at time 75, that I will make this very explicit here. 125. This is like the time when this first acknowledgement is received. So at the time 100, the acknowledgement is not yet there. So at the sender side, E4 has left. E4 is on its way. And package 1 timeouts at 175, packet 2 times out at 200, packet 3 times out at 225, and packet 4 is finally on its way. It timeouts at time 250. And what happens at the sender? Sender stops. Because there is no slot free in the sending window. So the sender stops. On the receiver's end, packet 2 is received. And as packet 2 is a sequence in the receiving window, we shift the receiving window by 1 position to the right. Packet 3 is lost, so packet 3 does not start to receive, but we send an acknowledgement for packet 2 back, and the time it arrives, it's 150, because currently we are at time 100, travel time is 50, so it arrives at the time 150. Let's do one more. Let's do 125. At 125, the first acknowledgement arrives. So this is acknowledged then. Nice. Because if we acknowledge the first packet, we shift the sending window 1 position to the right. 100, 5, 50. And now we can start transmitting packet 5. Start transmitting 5. Because now we have room in our sending window. What's the situation at the receiver? Well, packet 3 is lost, so it is not received. And packet 4 starts to receive. our window is this way. Okay. Let's continue until you are done. Are there any questions? No questions? Can I show you the whole page? Sure. The whole page is not filled out. Maybe this. I with the first, how many steps did I do? The first 6 steps, I have shown you how this question is done. And you're supposed to finish this at home. We will take a look at the solution next week. Interested in this. I'm moving my way myself out of the way. Then we conclude for today. Thank you very much for attending, and talk to you next week. Next week we have the last lecture. I will show you the solution for the sliding window protocol, and we will talk about network performance. Yeah. Good rest of the week, and talk to you soon. Bye bye.